Hello, if you have a question about physics, let me know. Hello, if you have a question about physics, put it in the chat and I'm happy to talk about it. Well, if you have a question about physics, let me know. You can put it in the chat. I'm doing good. How are you? Question: how does an object's mass affect its acceleration when you push it with a constant force? Tell me more. Can you tell me about an example or something like that you're thinking about? And if you can tell me like kind of your a little bit of background as well, so I have kind of an idea of where you are. So I don't want to explain things. Well, I want to explain things in a way that is understood. So, like, familiar with Newton's laws or no? That's the sort of thing I want to kind of understand. Okay, that's good to know. So, yeah, you're asking about the mass. There's Newton's second law that relates force, mass, and acceleration. And if you have a certain force, then it causes an acceleration to a certain object, right? So imagine, just think about an everyday example. Something's on the floor, you're trying to push something. If you push hard enough, you can get it to move, that sort of thing. But there's a proportionality. You can kind of figure from everyday experience that if you have, let's say, a lighter box versus a heavier box, right? So what we mean by that is it's got more mass. So then if you apply the same force to both, you kind of know from everyday experience that the one that has more mass is more difficult to move, right? So to get it to move in a certain way, like the other one, you'd have to apply a larger force, right? So F equals ma is maybe how you may have or may not have seen it, right? So that's a form of Newton's second law. that relates force, mass, and acceleration. So they're proportional. So if you have a certain mass and you apply a certain force, it causes a certain acceleration. If you increase that force, it causes more acceleration. But you can also have the same force applied to some object, and if you increase the mass, then you can only get less acceleration out of it, right? Does that make sense? Let me know. I'll go back and forth with me. Tell me if that wasn't clear. Happy to clarify. Question: what does a planetary physicist do? Good question. It varies on the subject. Generally speaking, planetary science involves studying planets, particularly in our own solar system. And why that is historical. It's so if you're studying planets outside of our solar system, it falls under astronomy, and people study exoplanets, right? So planets outside of our solar system. So typically, when you hear the phrase planetary science, it means planets in our own solar system. And planetary science is very broad. It can involve geology, chemistry, right? So you might be studying atmospheres, you might be studying the surfaces. Right? So it's a very, very broad field. What I mean by planetary physics is what I'm trying to say is something like astrophysics, right? So instead of focusing on, let's say, how do stars work, the focus is on how do planets work, right? So you're using physics to understand how a planet functions, right? So particularly with my case, I studied the thermal evolution of the moon. So what that means is that after the moon formed, it formed like this ball of lava, right? Like in Hawaii, you have lava that flows. So liquid rock, essentially. So the entire moon was likely made out of this lava, and the physics of it is thermodynamics, right? So how does this moon that's liquid cool off over time to become the solid moon that we have today, right? So that's applying physics to understanding how planets work, right? So hopefully that answers your question, but if you've follow-up questions, please ask away. Sounds interesting. Yes, it is very interesting. So yeah, it's very broad. So it can mean lots of different things. So it's not one thing particularly. So if you're into biology, right, planetary science is part of that as well, right? Because in particularly planets outside the Earth, of course, let's say Europa, for instance, is a moon of Jupiter. You will be trying to study, is there a possibility of life on this moon, right? Because there's water, liquid water in this moon. So can there be life, right? So it could be physics, it could be chemistry, it could be biology, geology. So the fundamental sciences all can be used to study planets. And so when you hear somebody is a planetary scientist, it can mean a lot of things. So you should ask them what they mean by that. Let's see. I know it's a basic question, but it's in a from a. So how does a huge boat float? Sure. So you're asking about buoyancy, and that's why like a boat made out of metal, right? They're very large ships, right? If you go on a cruise ship, for instance, they're very, very large and made out of metal, and it floats versus the coin, right? That will drown. So buoyancy is an application of Newton's laws, the kind of the F equals ma of it, and it can be a little confusing. And so the key idea of buoyancy is that if you put some object into a liquid, I mean, do this yourself, take a glass of water, put something in the liquid, there's a force upward that's there. And why is there a force? Well, that's because there's pressure that increases with depth. And last time I did this, somebody asked the question of why pressure increases with depth. And there's a video. So if you click on my channel, you can go see. There's a short segment I posted just on that topic, how mathematically you can get that, yeah, as you go down into a fluid, the pressure goes higher and higher and higher, right? So if you place an object, let's say, imagine there's liquid here. If you place an object inside the liquid, then the pressure on top and the pressure on the bottom are different because the pressure at the bottom is higher. So there's a net kind of effect of pushing the object up, right? So that happens with anything you submerge in a liquid, including air. Is I should say fluid, just to be kind of clearer. Air, it works in air, it works in, let's say, water, right? So whether it be a liquid or a gas, fluids generally, this concept applies. So there's that net upward push. Now, the question about what if something floats or sinks has to do with the effect of that upward push compared to the downward pull of gravity, right? So in certain cases, like if you take like a block of wood and you put it in water, it'll float because the force that the liquid, in this case water, can apply is quite high. So it can push really hard compared to the weight of the block itself, right? So the block will, yeah. So it's always a comparison between the upward push and the downward pull. In certain cases, when you see something floating, like the ship, like it's made out of metal, for instance, then you get this upward push that's much larger than its own weight, so then it'll float. So that's roughly how it works. I can show it to you more mathematically if you'd like, but that's conceptually at least how it goes. Okay, let's see. We talked about the boats. Okay, OSC countries trying to land on the moon. What's their end goal of these explorations? What the results unknown from these explorations? Yeah, broad question. In terms of the first part, why go? That has lots of reasons. I always promote the peaceful scientific purposes of going through this. So going to the moon involves understanding how the moon is, right? Currently, understanding what it is, right? What is it made out of? What are some of the things that are happening on the moon? Understanding the structure inside of the moon, right? So the layers of the moon, understanding where the moon came from, right? So all these are important questions because the Earth and the moon formed together, right? So there was the Earth a long, long time ago, 4.5 billion years ago. It was struck by something the size of Mars, right? So the aftermath led to the Earth as is now and the moon that we have. So the figuring out how the moon formed inherently involves understanding how the Earth formed, right? So they're linked together. There's also just the basics of understanding how things work. It's always good to understand how things work, right, at a fundamental level. Then in terms of kind of science you can do, there's a lot of science you can do that's essentially not related to the moon. You can, of course, do science about the moon, but on the far side of the moon, on the side we can't see from the Earth, for instance, you can put telescopes, like radio telescopes that are shielded, right? So we emit a lot of radio waves, so it's kind of noisy near the Earth. So when you're listening to signals from elsewhere, you kind of want quiet radio silence. So then you get that from the far side of the moon. So putting radio telescopes on the moon allows you to study the universe, right, more broadly. So there's lots of reasons. Not so peaceful and scientific reasons are, of course, taking resources, right, kind of for commercial purposes. There's military, people think about this, right? So going kind of carving out the moon for kind of like colonizing kind of thing idea. So I would promote science, peaceful purposes, trying to understand how the moon works over any kind of battle for territory. In terms of the results that so far, there's a ton. We know how the moon formed as a result of it, of, let's say, Apollo missions, right? So in the 1960s, the Apollo astronauts picking up rocks from the moon, allowing us to study what those rocks are, their properties, allowed us to understand how the moon formed, understanding impact craters, right? So the moon's full of impact craters. That's from these explorations, do we understand, oh, impacts are a very important part of planets, how they evolve, where they get bombarded quite a lot over their lifetime. And so we've understood impacts. So there's a lot we've understood. I can point you to different resources. If you shoot me an email, I can put my link to where you can send me a message. If you shoot me an email, I can send you lots of resources for you to see. I'll do that right now so that I don't forget. Oh, thanks. Yeah, so I teach physics now. I taught at the university level. I'm trying to now do this online. So if you have questions, let me know. Just put the link to my website. You can talk to me one-on-one if you want. I also periodically do these live YouTube live sessions just so that people can come ask me physics questions. So it's a fun topic for me. So I'm happy to answer questions. Yeah, happy to take questions. And if you want to see any kind of detail in terms of math, I'm happy to get into that. I will get into it once I get the conceptual answer through, because sometimes I think the math and the physics diagrams gets distracting, because I want to make sure, I want to motivate the answer by giving a conceptual answer. But if you want to know something a little bit more detail, happy to get it. My iPad's connected, so I can jump in and kind of write on it. From cybersecurity background, I don't know what I think about cybersecurity other than it's important, right? Yep. Happy to help. Yeah, check out the website. That's where you can find my contact information. There's a form on there, kind of like a contact form. You can just ask me questions, send me questions right there. Yeah, so then you can see my kind of background if you want. It's up there. And then, yeah, you're welcome to book time with me if you want to talk one-on-one. Happy to help there as well. Oh, yeah, question about Interstellar, the movie. Yeah, it's a good movie. It's been a minute since I've seen it, so I've probably forgotten a lot about it. Yeah, so it's cool. It's in terms of the physics I talk about, I stick to kind of the introductory physics, the kind of high school introductory physics at the university level, like your first year university level physics. Don't really cover black holes. It's part of relativity. So you need something called general relativity. It's our modern understanding of gravity. So in intro physics, you'll talk about Newton's law of gravity, which is very good. It is sufficient to put a person on the moon. That's all you need. It's very accurate, but it's not the full, complete understanding of gravity. So it falls short in certain ways. And so that's where general relativity, where what Einstein's version of gravity. That's where it's our best model so far. It's the best understanding that we have about gravity. It's also incomplete. All models are incomplete at some level, right? So yeah, so you really have to get into general relativity to understand black holes properly. You can kind of roughly understand what a black hole is using kind of simple quote unquote physics, right? And what a black hole essentially is an object, a dying or dead star, right? Typically, what you're talking about is a star that or died, right? In its aftermath, left an object that has mass. It has so much mass that its escape velocity exceeds the speed of light, right? So every object you can think of, let's say the Earth, has an escape velocity. So that means that if you have a rocket, you travel at a certain speed greater than that speed, you can escape the Earth, right? And that's how you go to the moon, go to Mars, right? You have enough speed to break away from Earth's gravitational pull. So the Earth has an escape velocity, the moon has an escape velocity, so you can look up the numbers. You can also derive it if you want and kind of come up with the numbers yourself. But if you think about object, well, what if some object was so massive, right, had so much mass that its escape velocity is so high that it is the speed of light, and our current understanding is nothing can go faster than light. So then the idea is, yeah, so there are these black holes, right, because they literally look dark, that nothing can escape once it's inside this area, right, that is the black hole. So yeah, so you can kind of get a rough idea of what a black hole is just by thinking about, okay, escape velocity, things like that. However, you're not going to get the detail maybe until you study general relativity. So not part of intro physics, so I don't necessarily get into all of that because I'm very passionate about getting people to understand intro physics first. And if more people understand intro physics, we can all, be happy and move on to the things that are more complicated. But I worry that a lot of people don't understand kind of the basics, right? So we need to our ABCs before we do things that are more complicated. So fun topic, but yeah, it's something I don't talk about here. Okay, best books to learn physics for aspiring scientists. Um, that's a hard question. Can you maybe add some detail to that in the sense of what do you mean? Maybe your academic level, are you in high school, you're in at the university level? Because I can recommend, so the one place I would definitely say go to is the OpenStax books. I'll put the link to OpenStax. So if you have not seen these, there's our free textbooks that are open source, freely available. It's peer reviewed, so it's not like some random people on the internet are writing this. So they're written by people who know what they're talking about. And there's all sorts of subjects, including physics. So it's free, right? So you can download the PDF. You can view the textbooks for free online. If you want to buy the physical copy, you can pay for it and they'll ship it to you. But yeah, that's a good place to start, particularly physics, I think, and ask questions as you go, right? So get into it. If you're just starting off, let's see, in the OpenStax physics section, they have something called physics, and tiny font. You can probably see high school written on it. So that's probably the first level to start with if you've never ever seen physics before. If you look at the next set they have, it's called college physics. There's also one with AP courses if you're in high school. So just FYI, when people say college physics, what that means is they're talking about physics at the university that's algebra based, right? And when they say university physics, typically what that means is calculus-based physics, right? So yeah, I would maybe if you are in high school, try the high school one, just the one that's just called physics. If you're entering or pretty close to going to college, going to university, Try college physics if you want the algebra one, or try university physics. The university physics, they have it in 3 parts because it's a giant book, so they broke it into 3 parts. And as you read through it, if you get stuck, send me a message. You can ask questions. That's a good place to go. The other place is, you probably know, Khan Academy. If you want kind of more video-based learning, let's put that there as well. So that's Khan Academy. Yeah, so both are pretty good, very solid resources to get started. But I think, yeah, the best way is just get going and ask questions as you go, and you'll learn. Okay, best books. Okay, what are the topics in intro physics? Yeah, if you click on the OpenStax, one of the books, you'll see how the book is organized, essentially how the topics are broken down. Physics at the university level, if you're doing the semester system, first semester called Physics 1 is mechanics. So you start off with talking about kinematics, how things move. Then you get into something called dynamics, which is Newton's laws, the forces, right, accelerations, things like that. And then you talk about work and energy. You'll talk about momentum, right? So things like collisions. You'll talk about rotational motion, so moments of inertia, how things rotate. And yeah, we'll get into thermodynamics. So there's some set of topics that you typically covered by Physics 1. Physics 2 is electricity, magnetism, and optics. Pretty much standard. Physics 1 tends to be a little bit more different depending on which university, which course you take. Physics 2 is pretty standard except for maybe the order of topics. So some people will start talking about optics first, which is light, right? How light travels, lenses, mirrors, right? Things like that. So some people will start with that first, go into electricity, then cover magnetism, and then talk about electromagnetic waves at the end. Some people cover lenses and mirrors at the end. But other than that, it's the same set of topics for physics too, largely. So yeah, if you click on the books, the OpenStax books, how they lay it out is pretty standard. It does vary from professor, from teacher to teacher. They vary things, but intro physics is pretty standard these days. How do you pick a domain to get into in the sciences? Yeah, science is a very broad topic, right? Generally speaking, and how you get into it is, I think, just by whatever you're interested in, right? So just think about what topics are just interesting to you, and then think about, okay, who studies that in more detail, right? So to me, uh, like, I had a kind of a strange path into physics. It wasn't something that I just knew as a right away that I was going to go into physics, but and particularly physics education. How I got started, particularly at the university level, was to think about, hey, what am I interested in? I'm interested in things that fly in space, right? So that became aerospace engineering. So that's how I started in at the university level. I wanted to help understand, build things that fly in space, right? So people who do that are aerospace engineers, typically, not always, but it's typically that's who does that job, right? So then I went into that to try to understand that, right? And along the way, as I was doing engineering, that's when I kind of really got into physics, because I realized, oh, that's really cool. It's elegant. There's so much structure and kind of detail to it that if you understand physics, you really can understand a lot of things, right? Because that's the kind of the foundational science, if you will, right, of understanding everything, everything in the universe, literally. So yeah, so I would encourage you to do what you're interested in. So if you want to throw in what you're interested in, I can kind of maybe point out what area that might be in the sciences. But yeah, science is a very broad term, of course. Yeah, I think if you're in, so you're in computer science and you want to study physics, start with the OpenStax books or the Khan Academy videos, right? So just start somewhere, right? And it's, yeah, start with kind of kinematics and Newton's laws and things like that, and as you progress you'll understand more. It's not something you can just jump into the middle of. So it's something that you have to really understand the foundational material before you can understand something else. There are other fields, of course, that if you want to understand this aspect of it, you can kind of ignore the rest and say, okay, I'm just going to focus on this, right? And I'm going to understand it. I can pick up a book about that thing and then just focus on that. I don't have to necessarily go through all of it. Physics is not like that, where there's all these little concepts that's built on other concepts, which built on other concepts, right? And then math is involved. So there's concepts in math that are come into play as well. So yeah, it is something that is, yeah, that requires you to kind of go in a certain order to really understand it. You can kind of watch a video on YouTube and have, oh yeah, yeah, I kind of know how it works. But if you really, really want to understand it, and especially, I think, in my opinion, you understand it when you can draw things out and write equations and solve the problem on paper, right? That's when you really understand it. If you can say something conceptually, like at the beginning we were talking about buoyancy, and so you might be able to say, oh yeah, buoyancy has to do with this pressure varying with depth, right, in a fluid, and you might be able to say that, but to really understand it, you need to draw a diagram and write some equations, things like that, right? Okay, hopefully I've answered all the questions that are there so far, but if I missed anything, please copy paste and put there again. I think I got everybody so far. Yeah, so remember each planet has a different gravitational pull, like the moon has 1/6. Yeah. So you're talking about the acceleration due to gravity. So if you drop an object on Earth, it will accelerate to the ground at 9.8 meters per second squared. So that's kind of the rate at which things fall. So that has to do with the mass of the planet and has to do with how far away from the planet you are, right? So yeah, so the size of the planet matters, the mass of the planet matters too. So the moon is smaller and also has less mass, so its values can be smaller. So same thing for Mars, right? So it's a smaller mass than the Earth, is physically smaller than the Earth. So the acceleration due to gravity on Mars is smaller, right? Yeah. How does the gravitational pull affect other properties? Other properties like what? Just put some ideas of what do you mean? And I'm happy to answer. How do you keep all the formulas in your mind all the time, especially in complex? Yeah, so I don't. Is the short answer. I don't memorize formulas. It's so in physics, you want to try your best not to memorize. It's different when you're talking about biology. So if you're a biology student, please memorize, like do what your professors and teachers tell you to do. But in physics, don't do that, right? So if you're learning a language, like let's say you're making flashcards, I'm learning Spanish, so I make flashcards and I have to kind of memorize, right? I have to say this word means this word means this, right? But in physics, it's not going to help you. It's actually going to hurt you a lot of times when you try to do that. So when I teach, I allow students to have a formula sheet, right, on an exam. Not everybody does that. But what you could do if you don't get to have a formula sheet on an exam is from day one of the class, make yourself a formula sheet, right? So as you're going through the class, what are the formulas that the professor instructor is talking about? Write those down. Not all of them are the most fundamental, and if you're not sure, go ask your professor or teacher, right? That, hey, is this a fundamental physics equation? There's many equations in physics that are derived, right? So they come from other things. So it's less important that you memorize every single thing that can be coming out, because then it's too many, right? You're not gonna, but you can remember the really fundamental ones, right? So as you're making a list of these and you're doing your homework, as you use them, it'll go to your memory eventually, right? As you use them, and you're actively using them, and you're doing your homework, you're doing some practice problems, it will go to your head. Trust me, it will. It just takes some time, right? But yeah, try not to memorize a whole lot, and frankly, you don't really need to memorize a whole lot. Um, there's always the joke that physics has only a few equations that you use, but the trick is you use it 100 or 1,000 different ways, right? If you look at a lot of physics problems, it's the same equation, it's the same idea, but it appears to be this whole new problem that it isn't. It's the same problem, right? So if you understand, oh, this problem really is about Newton's laws, or this problem is about work energy, the work energy theorem, then you just kind of, as you kind of shortcut into the problem solving, because you kind of recognize, oh, this is this kind of equation. So I generally map out how these equations come from different places. So if you look on my YouTube channel, there are videos. So I'm posting more of my lectures that I've done in the past. So as you go through them, you'll see I kind of connect the dots, and I show you, oh, this equation came from this, right? So you can kind of understand where they come from. So you kind of have a map in your head. So you don't see this disconnected set of 100 equations, right? Where you're seeing is, in some ways, one, two, three ideas applied in different ways. So physics one, mechanics, I would argue, is just two ideas. One, how force and momentum are related, Newton's laws. And the other idea is how energy and work is related, right, to each other, right? These are two ideas that are connected to each other. So the entire class is just two ideas, right? But if you look at a final exam for physics one, it looks like a lot of stuff, right? But at the end of the day, it's really two things, right, that is popping up. So you can get those ideas, and then you really don't require a whole lot of memorizing. So okay, I'll answer your second question too. I really struggle in physics where complex math involved. Can you define like complex? You mean calculus, or like what do you mean by the complex math? So if I know where you're coming from, yeah, calculus. Um, yeah, are you taking calculus, or you've taken it in the past? Because if the so with physics, one of the things, a big part of the struggle for students is math, right? It appears to be physics. A lot of people go, "Oh, physics is hard," and I have seen a lot of students. I've taught over 5,000 students at the university level, so like. I've seen what the struggle is. It's not necessarily the physics that's tripping people up. It's the math. So if you're finding it's the math that's kind of confusing things, take a moment. It might appear to be, oh, I need to go, step away from physics, and then spend some time with math. But it's only going to help you if you fix those issues with calculus, let's say, right? So you say, love physics but struggle with math. So yeah, I'm in the same boat a lot of times, right? So the math to me also is a struggle. So think of math as a very useful tool, right? It is kind of the language of physics. So it's not that you're going to be able to do physics without math, and not well, at least, or not at the level that you want. If you try to do physics without math, then you're just going to be at a conceptual level where you're going to just kind of have a surface level understanding. So to understand physics, to get really into it, you need more math and more math and more math. And as you get deeper and deeper into physics, we were talking about general relativity, right? The modern model of gravity, it requires a lot of math, right? So it requires something called tensors, right? So it's a, think of a tensor as a fancy matrix if you've seen a matrix. But yeah, so the deeper you go in physics, the more math you need to learn. And I wouldn't treat that as something to be intimidated by. I would take it as you go, right? So learn the math as you go with the physics. I wish, for instance, physics and calculus are taught together, or you're expected to take those side by side, right? A lot of times students take calculus maybe last year or a while ago, and then they take physics. And I think if they were taught together and you took them together, you kind of see the value, right, of the math, right? The calculus, why a derivative makes sense, right? Because yeah, the physics help. So I think as you're learning physics, improve on your math, right? So as you go through, oh, I need this new math concept, you need to spend some time with it, right? There's no way around it. It's something that's important, and it's okay. It's good to take some time. Say, okay, I'm going to spend some time understanding integrals or whatever that may be, right? So it's actually very good. Yeah, so getting it better. So likewise, as earlier, OpenStax, it's should be, if it's not showing up for you, let me know in the chat. But up in the chat, I posted a link to OpenStax, which is a free set of textbooks, peer reviewed. It's high quality. I use it when I teach at the university level. So this is not some, kind of freely available, kind of not so good textbook. These are very good textbooks, and they're freely available. You can click on the PDF and download them. And I would start there. They have, so I think the link I posted is just for the science, but if you go on their website, there's a whole section on math, algebra, trigonometry, pre-calc, calculus. They have textbooks for all of those subjects. Go through those, right? And it's important to read through. I know a video helps, right? But yeah, so Khan Academy I listed as well. So like videos on YouTube are good. Definitely there's some really good stuff out there, including Khan Academy. But don't substitute that away for reading. Reading is important too. So when you have a textbook, really spend some time with the textbook. I know it takes a while to read, yes, and time is limited, but yeah, reading is really important. You just learn better and more thoroughly, right, when you read. So these are all passive ways of learning: reading, watching videos. These are all passive. You want active ways of learning as well, right? So that means doing a problem and putting yourself in a situation. So if you have a study buddy, you both can get together and challenge each other. So pick a random problem and say, hey, you do this in 10 minutes. I'm going to do this other problem. And then you can collaborate, right? So put yourself in the spot, right? So if you're, let's say, learning a new language and you're going through Duolingo or something, and then you go to another country and then you try to talk and then you struggle, right? So when you try to apply, that's when you actually know if you understood something, right? So put yourself in that active setting as well. Passive stuff is good. Don't say, I'm not saying passive ways of learning is bad. Reading, watching a video, you're just consuming, right? You're taking in information. But active means you're actually trying to solve a problem yourself, like an exam, right? So when you have an exam, that's what happens. So both are important, right? So try to do both, and then the more practice you do, the more you practice, the better you get it, right? Yeah, so hopefully that'll yeah. Okay, yeah, the math is like an ocean that never ends. Yeah, I mean, you're spot on actually, because math, when you think about math, what is it? It's this very broad thing, right? We can kind of think of it as a language, but it's not really a language. It's many, many, many languages that we group together and call math, right? And there's lots of kinds of math, right? So there's algebra, and there's calculus, and there's tensor, right? Dealing with tensors, vectors, right? So all these things are different kinds of math. And so one of the big things about math is having a set of rules that are consistent. They're very logical, right? But you can create set of rules all day long, right? So people who are more theoretical in the math world, they can create different kinds of math that are self-consistent. They follow a certain logic, right? So it's never ending, literally, right? But the kinds of math that are useful in physics, right, is a subset of all the math that's available. It's not that we use all of the math that's available. We use some of it, right? So that's what I mean. Just when you're learning physics, go with what's required for that topic. So when you're talking about first year physics at the university level, big thing is calculus, right? If you're taking the calculus based one, if you're taking the algebra based one, of course algebra, right, and trigonometry. So these are the things that are really relevant. Tensors is not relevant; they're not relevant, right, in the first year of physics. So go with what you're doing at that point in time, and then it'll come, right? Let me try to catch up. I think there's a few questions maybe I missed. Okay, there's a question about why do planets not collide even having huge mass? Is it because the distance between them? Remember former. Yeah, so planets did collide, right? Back in the early days of the solar system, there were a lot of collisions, right? They were running into each other constantly, not at this size. So how the planets formed was in the early days of the solar system, 4.5 billion years ago or so. The sun's forming in the middle, and then there's a bunch of material that's surrounding it, so gas and dust, and they start clumping together, and then these clumps get bigger and bigger and bigger. So eventually, you have fairly large size things. Let's say the size of asteroids, the size of Mars, right? These are the objects that are kind of floating around, and they do collide with each other quite a lot. And in the collisions, some get even more massive because they acquire more mass that way. And eventually, the solar system gets pretty quiet because there's only a few things and they don't always run into each other, right? So if you look at the solar system today, if you look at how many planets are there, right? So there's only a handful of, or two handfuls of planets that are there. But imagine a time when there were 100 different little smaller chunks that kept running into each other. So these days, yeah, they're far enough apart. They follow a certain orbit, right? So they don't really intersect each other now, right? So they're kind of more quiet now these days. But yeah, early days of the solar system or any kind of planetary system that's forming, right? In the early stages, lots of collisions. Okay. Can I speak Hindi? No, I don't. I know English and I'm trying to learn Spanish. I can understand Sinhala a little bit. I was born in Sri Lanka, so I can understand Sinhala a little bit. That's I can do a little bit of American Sign Language, but that's it so far. Does your job? I used to do research. So if you look on my website, you can look at my CV, and then you can see my publications. So I have done research in planetary science, studying the moon, studying asteroids, things like that. I've also done research in education, so more like educational psychology kind of work. And so you can check on my CV. You can see my previous work. These days, I don't do research because I really care about teaching. I think it's really not to say research is not important. I just want to focus on teaching because I'm very passionate about it. I think it's really important. I think there's a severe lack of understanding of science in societies these days. So I want to focus on that these days. Do you sometimes feel depressed that we'll probably die before we get to know about our own existence? Maybe. Life is short, but the nice thing is that we pass on the knowledge, right, to future generations. Think about the things that we kind of know today. Newton's laws, for instance, that was hundreds of years ago, right? So, and I think Galileo and all these people are from literally hundreds of years ago. So it's, you do some work, you have some understanding, you pass it on to the next generation, and I think that's a great thing, right? So you don't really see the full story, I guess, right? Which is, you're just contributing to the larger kind of understanding. So in that way, it's not that depressing. Maybe it's somewhat depressing, but it is kind of a cool thing. What do you think will happen after we die, according to science? I don't know if there is a scientific answer per se. I don't know enough about biology, so you want to look into that yourself. And if you do find out, let me know. A lot of work on neuroscience. I think one of the things to understand is consciousness, what causes consciousness, right? So, yes, we have a brain. Yes, our consciousness is in our brain. It has something to do with electrical signals that are getting sent through your neurons, right? So that creates this idea of a consciousness, that you're aware of your existence. When you go to sleep, it kind of goes away, sort of, unless you're dreaming, right? So when you die, that the electrical signal stopping should mean that your consciousness stops, right? But that's my very, very limited understanding of neuroscience. So check out like people, go on YouTube, go find people who do neuroscience kind of research, and I'm sure they have some thoughts on what happens when you die to like break to your brain. Um, yeah, I mean, grades are understandable. It's part of the system, right? The educational system. However, yeah, it'd be nice, yeah, focusing on the material and having a thorough understanding, as opposed to just getting an A in a class, right? So yes, it's good to get an A in class. And who doesn't want an A in a class? But I think as long as you're also learning, right, learning the material. Yeah, so once we're dead, can't become ourselves again. I suppose that's true. So, but again, go talk to somebody who knows neuroscience and biology. They'll probably have a more complete answer for you. Do you give A grades? You mean A grades in the class? Like generally? Yeah, I do. Um, yeah, I don't grade on a curve or anything like that. I tell students, this is what I expect you to do to get an A in the class. This is the level of understanding you're supposed to have. And if everybody gets there, everybody gets an A, right? So it doesn't bother me. But as long as they're doing the learning, right? So as long as I can say, oh, yeah, all these people learned the material at that level, then okay, cool. Everybody can get it. But it's not that everybody just gets assigned an A, right? It's not like that. Some people not get the A, some people get a B or a C or whatever it is, and so then of course they're not happy about it. But my question always is, did you learn the material at the level that is an A, right? So there's a certain level of understanding that's kind of an A level understanding of the material, and there's kind of a B level understanding of the material, right? So yeah, it just depends on what your understanding is at the end. Okay. Other questions about this? I'm gonna step off in a second here. I'll do these again. I want to keep doing these. I think they're valuable. It's useful for everybody to come in, just pop in and ask questions. So I'll do this once in a while, maybe once a week. I might try to do it twice a week or so. My website's on the chat. I will post it again. It shows you how to get in touch with me. You can also book a time to just talk to me one-on-one if you want to do that. So that way we're on Zoom essentially talking to each other. So we can do that. But yeah, I'll also do YouTube live stuff as well. Yep, no problem. Happy to answer questions. Any other quick questions? Other useful websites. What else can I think of? Yeah, OpenStax is good. Khan Academy is good. If you want, let's see if I can find three blue, one brown. For kind of maths, physics things, three blue, one brown is a YouTube channel. He's very good. Just post the link right there. That's a lot of detail. So once you are kind of interested in a certain topic and you want to know more, he does a really good job of getting into the details, like really in a very beautiful way. His animations are really, really nice. But there's a whole bunch, right? So there's on YouTube, there's quite a number of things. But if you're having trouble with finding resource for a particular topic and you're looking on YouTube and you're getting stuck and it's like there's no good resource for something that you're looking for, yeah, send me a message on use the contact form on my website, and you can send a message that gets emailed to me, so I can email you back with, oh, okay, you're stuck on buoyancy, whatever, and you're having trouble finding a good resource for that. I can send that to you. Yeah, that's the internet. So there's a lot of resources. I think that's one of the problems of the internet where there's a ton. So then what people do is then they'll curate a set of resources, but then I feel like that also gets very long, very easily. Like if you list all the YouTube channels that are talking about science or even physics or math, right? It's just a lot. So I think I wouldn't worry too much about finding the best resources right away. Try to find somebody who's reputable, who knows what they're talking about. Don't just believe some random person on the internet. Check their credentials. Ask for their credentials. Like, where did they study? What did they study? Right? These are fair questions to ask. So just make sure you're listening to the people who actually know what they're talking about. But even then, there's a lot, right? So that's really becomes preference and taste, and you like how this person presents the information versus that person, and that's fine, right? So that's okay. Yeah, pretty much. Yeah, like those are the things that I kind of recommend to the students. The OpenStax, Khan Academy, um, yeah, those are pretty sufficient. And then get into those things and then ask questions as you go. Right, feel free to send me a message and ask me questions. It's just getting started is the big thing, right? So it's not about, oh, I need to figure out the best resource for this. It's get started somewhere, right? And it's somewhat of a productive struggle. It will be a struggle. It's not going to come easy. Not, things when you're learning something new, it's not going to come easy, right? So, like I said, I'm learning Spanish. Does it come easy? No, of course not. It's a struggle, right? But because if you think about how do I learn Spanish? Well, there's websites and there's books and there's so many things. And so at the end of the day, it's a matter of start somewhere and then oh yeah, this is working, this is not working for me, right? Then you can make some adjustments. Talk to people at the end of the day, right? I think one of the things with the internet is people relying too much on resources or websites that are kind of static. These things exist. So if you can talk to somebody either in person, online, whatever, I think it's easier to get something resolved, right? Because otherwise you're stuck and you're struggling. Somebody can help you, right? So whether it be somebody in your class, somebody as a teacher, right? Get connected with people, I think is really important, right? Okay, sounds good. Yep, I'll host these again. I'm on social media. It's on my website, so I'll post everywhere when I'm going to do it. Like I said, maybe I'm shooting for at least once a week. I'm going to try to do twice a week, and maybe go from there. This is the second time I've done this, so yeah, I like the format. I like the questions, so I like doing this, and so yeah, I'll definitely do this going forward some more. And yeah, on my website, more information on how to get in touch with me. Right. Thanks, everybody. I'll talk to you soon.